In this subsection, we start to construct a table of Z transforms that we can use in the exercises, and we'll start with the discrete unit impulse delta K. So the Z transform is defined in this fashion, and what we do over here is use the shifting property. Well, the delta is located in K is equal to 0, so this means that we can replace K here by 0, so this is 1. So we end up with a sum of deltas, and of course there is only one delta that is going to contribute, the one located in 0, so this is why we have 1. There are no conditions on Z for this sum to converge, so the domain of convergence is the whole Z domain, right? Now I want to insist that if the signal has finite support, this is clearly the case for the unit impulse delta K, you can always use the definition to obtain the Z transform, and the definition is the following one. It's a sum where K ranges from 0 to infinity of f of K Z minus K. So this means f0 Z minus 0 plus f1 Z minus 1 plus f2 Z minus 2, and so on. So in this case here, if you draw the graph of the impulse, the unit impulse, this is what you have, right? So in this sum there will be only one term that is contributing, and it's the first, so it's immediate that the Z transform of the impulse, the unit impulse, is delta 0, which is 1, Z minus 0, 1 also, so it's kind of immediate. Okay, so if you have a general function that is of finite support, for example this one, then it's very easy to obtain the Z transform of that signal, right? So we'll assume that this is 1 here and this is 2. Then it's simply 1 Z to the power 0, so 1, plus 2 times Z minus 1, this is this term over here, plus 2 times Z minus 2. So in the exercises that you will have to do, very often, instead of clearly specifying f of k mathematically, it's shown using a plot. Okay, so you have to be able to construct the Z transform, and the easiest thing is just to use the definition. Well, the next function is the unit step. Remember that the definition of the Z transform is the following one. And what we will need over here is this geometrical series. It's a sum that ranges from 0 to infinity of q to the power k, and it's 1 over 1 minus q, but we need the assumption that the modulus of q is smaller than 1. So if we use the definition and apply it to the unit step, this is what you obtain. Of course, the unit step, it's 1 for k positive or 0, so you end up with this expression. And now what you can do is apply this formula. Okay, z minus k, you can see it as z minus 1 to the power k, right? So here q will play the role of z minus 1. So you end up with this rational function that you can rewrite also as z divided by z minus 1. You will see in the course that often we will work with the variable z minus 1, and in other cases we will work with the variable z, right? Remember that, well, this sum is valid only if the modulus of q is smaller than 1. So in order for this to be true, we need here also that the modulus of z minus 1 is smaller than 1, which is equivalent to the modulus of z larger than 1. So the domain of convergence, the region of convergence, is outside the unit circle. Okay, so another way to obtain the region of convergence is to have a look at the pole, and the pole is located, this will be the unit circle, so the pole is located over here. Okay, so we know that what you have to do is take the pole with the maximum radius. Clearly, since there is one pole, it's, well, the pole in 1, and then you draw a circle on that, and it will be the outside of this circle, and this is the region of convergence, and this is also what we had obtained using this condition over here. Also notice some similarities with the Laplace transform of u of t. It's 1 over s, right? You have a pole at the origin, and if you look at the relation z is ETSS, and so here the pole is at the origin. If you plug that in, you have a pole indeed in z is equal to 1, and also the domain of convergence was sigma larger than 0, and if you remember, well, sigma is equal to 0, the j omega axis is mapped to z is equal to 1. Okay, so the being to the right of the j omega axis will become, well, being outside of the unit circle, z is equal to 1 in the z domain. So clearly there are some analogies. Well, let us have a look at the z transform of discrete complex exponentials of the type that is shown over here. So we'll do this in general for alpha that can be complex. So by definition of the z transform, this is what you obtain. Remember that, well, the unit step here for k positive or 0 will produce a 1. So alpha k z minus k can be rewritten as follows. And why did we write it like this? But this is because we want to use this formula 1 over 1 minus q, and remember that the modulus of q should be smaller than 1. So this is playing the role of q over here. So this is what you obtain, and again this you can rewrite also as z over z minus alpha. This step from here to here is valid only if, well, q is smaller than 1 in modulus, so alpha z minus 1 in modulus is smaller than 1, and again this is equivalent to the modulus of z larger than alpha. So the region of convergence is outside a circle of radius, okay, the modulus of alpha. Okay, remember here that alpha can be a complex number. Okay, another way to obtain the region of convergence is to have a look at, well, the pole. Okay, suppose here that alpha is real, that you have your pole here in alpha 0.5. What you will do is, well, you have a radius of 0.5 here, that's the maximum radius. Since we have only one pole, you construct the circle on that, and the region of convergence is outside that circle of radius alpha, right? And this is indeed consistent with what we had found over here. So let us look at this a bit closer when alpha is real, right? Remember that we had here z over z minus alpha. This is another way to write the z transform, and let us have a look at what happens first when the pole is real but positive. Okay, so this is the z domain, so this is the unit circle. Modulus of z is equal to 1, and let's take the case where we have a pole at alpha is equal to 0.5, and let us take another case where the pole is larger than 1, let's say 1.1. And let us have a look now at the corresponding discrete exponential, real exponential here, because alpha is real. So we can draw this. So the x-axis is the index k, and this will be f of k, right? And so let's see what happens here when alpha is equal to 0.5. So 0.5, of course the sequence is causal, so we'll have zeros over here. In k equals 0 it's 1, right? And then in k equals 1 it will be 0.5. In k equals 2 it will be, well, 0.5 to the power 2, 0.25, and so on. And you see that if you continue, well, you have something that is exponentially decreasing. Okay, this is corresponding to a pole that is inside the unit circle, and you'll have to make the link with stability later, right? So we can now have a look at what happens if alpha is outside the unit circle, so it's positive and larger than 1. So obviously the sequence is still causal. You start from 1, then 1.1 to the power of 1, it's, well, 1.1 to the power 2, well, it will be increasing, and you see over here what you will have is something that will be diverging. It will be exponentially increasing with increasing k. So this case will take alpha real and negative, so we can still obtain a different expression of the z transform if you use the variable z. We'll again show the z domain with the unit circle. modulus of z is equal to 1, and in this case we'll take alpha negative. So we'll consider a case here at minus 0.5. Okay, so this is alpha is equal to minus 0.5, and we'll consider a case here where alpha is negative but its modulus is larger than 1. So you're outside the unit circle, and you can kind of imagine that this will lead to a sequence that is, well, unstable, diverging. Okay, so again we can have a look at the response. So this is f of k. We'll start again with the pole here that is inside the unit circle but with alpha negative, and so this corresponds to this case where alpha is minus 0.5. You can see here that the sequence is causal, so of course you'll have zeros over here. In k is equal to 0, you'll start with a 1. Alpha to the power 0 is always 1, and then at k is equal to 1, you'll have minus 0.5. So this leads us to something that is negative. When k is equal to 2, you'll have 0.25. And here something negative. So you see here indeed that the signal alternates sign, but if you would take the modulus, you still have something, right? If you draw it, it's still something that is exponentially decreasing. So this corresponds to the case where alpha is negative but inside the unit circle. So let us have a look at the case where the pole is at minus 1.1. Again, it's a causal signal, so you have zeros over here. In k is equal to 0, you have a 1. Then in k is equal to 1, you have minus 1.1. k is equal to 2, well, you have something that is, well, approximately here, and then here. So again, you have these alternation of signs, but you have something that is globally diverging, and we will see later that it is linked because to the fact that the pole is outside the unit circle. So let us now compute the Z transform of this type of signal. This is a signal that we have encountered in the previous section. It's a, well, sum of two complex exponentials. It can be written as a alpha k plus a alpha k conjugate. Okay, so in the exercises you will not encounter Z transform of this type of signal, because otherwise it's a bit too difficult without the tables at your disposal. But you have to be able to make the link between, well, this type of signal and the poles of the associated Z transforms, and this is what we'll show right now. So again, you can use Euler's identity to rewrite this signal here as follows. Okay, so it's an exponential plus, and that is counterclockwise, plus an exponential that is clockwise, and then you have this factor 1/2, something that we have encountered quite often. This you can rewrite as R0, exponential of j omega 0 to the power k, right, times exponential of jv, and this one you can rewrite it as R0, exponential of minus j omega 0 k exponential of minus j phi. Okay, so indeed what we have shown is that you can rewrite it like this over here, where a is equal to a half exponential of j phi, right, and alpha is equal to r0 exponential of j omega 0. So what we can do now is use the z transform of this type of signal, where alpha k can be, remember, complex, and this was z over z minus alpha. What we'll use also is the linearity of the z transform. We have not talked about this linearity property, but of course the z transform derives from the Laplace transform, which is itself a linear transform. So we will use this to obtain the z transform of this signal over here. So it's 1/2 the z transform of this signal over here, right? So this will play the role of alpha, right? So what you have here is z times this one over z minus alpha, and here you have something similar. And what you can now do is put everything under the same denominator, and you obtain the z transform of this signal over here. Okay, so you do not have to be able to do this, but what you have to see is the link between this signal and the poles. Okay, well, the poles are z is equal to alpha, and well, you should not write z. So the first pole will be alpha, and the second pole will be alpha conjugate, right? So the poles are r0 exponential of plus minus j omega 0. Okay, so they are clearly linked with the alphas that you have over here. You can of course also look at the region of convergence. So let us draw the z domain, and this is the unit circle, and we have two complex conjugate poles. So this is r0, right, and this is omega 0. So to obtain the region of convergence, you take the maximum radius. So obviously here it's r0. You construct a circle. Okay, so it's this circle over here, and the region of convergence will be outside this circle. So indeed we see that the region of convergence is the circle outside the circle of radius r0. So there is a 0 lacking over here. In conclusion, this is what you obtain, and of course it allows you to obtain the z transform of a cosine and sine. So obviously you will have to consider r0 is 1 in both cases. The cosine will correspond to phi is equal to 0, obvious from here, and the sine will correspond to phi is equal to minus pi over 2. And of course the region of conversion is outside the unit circle. You simply have to replace r0 by 1 over here. So again, you don't have to be able to find the z transform of this type of signal at the time of the exam, but you have to be able to make the link with this, between this signal and the pole location. So we'll look at two examples, right? So I'm drawing here the Z domain, and I'll do it again over here. And this will all be illustrated again later on in the course using animations, but I want to make a first explanation. So in this case here, we'll assume that omega 0 is fixed, right? So omega 0, it's a direction, right? And so we'll consider two poles, one that is over here, so the radius is 0.5. Obviously there will be a complex conjugate pole over here, and the other case will be, well, a radius that is 1.1, right, and the equivalent complex conjugate pole over here, right? And in this case we'll assume that R0 is fixed, and we'll take it smaller than 1. So let's for instance take 0.5. So this means that you're living on a circle of radius R0, right? And what we will do is, for instance, consider two omega zeros, this one here, and for instance this one over here. Of course you'll have the complex conjugate over here, and you'll have the complex conjugate over here. Okay, so by looking at these here, it's not drawn very well, it should be on this line over here. So by looking at the pole locations, you can kind of imagine what will happen if you look at this signal over here. So let us take here the case of the two complex conjugate poles in blue. Since the radius is smaller than 1, it's 0.5 here, what you will have here is a cosine at a certain frequency that is, well, dictated by omega 0, but that will be modulated by something that in this case will be exponentially decreasing. If you now take the case of the two complex conjugate poles in red, you'll have the same frequency, but you will see that this cosine is modulated now by something that will be exponentially increasing, right? So here R0 is fixed, okay, R0 is smaller than 1, so you can see that the envelope here will be exponentially decreasing, but you can see here that the angle omega 0 is smaller in the blue case than in the red case. So you can see here that omega 0 will increase the discrete frequency of the cosine. Okay, so this you have to be able to do, make a link between the pole location and the type of complex exponential signal that you will have. As announced before, the Z transform is a linear transform. This linearity property is inherited from the Laplace transform. Given the Z transform of the sequence f of k and the Z transform of the sequence g of k, you can obtain the Z transform of a linear combination of these sequences, and this Z transform is simply obtained by taking the same linear combination of the Z transform of f of k and the Z transform of g of k. The region of convergence of this linear of the Z transform of this linear combination is simply the intersection of the regions of convergence of the Z transforms of the sequences f and g. What we'll do now is obtain the very important property for time shifting. So we are going to compute the Z transform of a time shifted signal, knowing the transform of the original signal, and this is going to be important when we solve difference equations. So this is how the initial conditions are going to enter into play, and this Z transform of a time shifted signal plays exactly the same role as the Laplace transform of a derivative of a signal in the Laplace domain. Let us first consider shifting to the right. We have the Z transform of the original sequence. Remember that f of z here is a sum where k goes from 0 to infinity of f of k z minus k. So now we consider the Z transform of the shifted signal. So by definition of the Z transform, this is what you obtain. We can now do a change of variable. N is equal to k minus k0. So this is going to give here an n. Obviously k is going to be n plus k0. So you can plug this in over here and you'll end up with z minus n plus k0. You also see here that k ranges from 0 to infinity. So if you plug this range in here, you will see that n ranges from minus k0 to infinity. What we can do now is decompose this sum in two terms, one that goes from 0 to infinity. This is because we want to recover here the Z transform, right? So we have one term that is the sum from 0 to infinity, and then observe that the z minus k0 does not depend on n, so you can take it out. So here you have the Z transform of f of z, right, of the original signal, times z minus k0, and then you have here an additional term that covers all the terms that have not been covered in this sum over here. So it goes from minus k0 to minus 1. The Z transform of the time shifted signal to the right has the same region of conversion as the original signal. What could happen is that sometimes you have to add a little additional restriction in z is equal to 0, but this is rather a technical condition, not so important. You can see also that if the initial conditions are all 0, okay, this term will disappear and you're left with this equation over here. In the exercises, and also in the exercise that you'll have at the time of the exam, you'll have to use this formula, but with k0 is equal to 1 and k0 is equal to 2, right? So let's apply this. So we assume that we have the Z transform of the original signal. So the Z transform of the shifted signal by one index is, well, this is f of z, right? It's z minus 1 f of z, and in this sum there will be only one term. It will be the term that will be corresponding to n is equal to -1, right? Because k0 is 1, so there is only one term. So what you'll have is f of -1, and here you have 1 minus 1, so it's z to the power 0, so this is a 1. So let's do this for a time shift of 2 indices to the right. So here it will be z minus 2, f of z. So here there will be in this sum two terms. There will be the term corresponding to n is equal to -2, and the term that will be corresponding to -1. Let's start with the one that corresponds to -1. So you'll have f of -1. K0 is 2, n is -1. Okay, so this is giving 1, so it's z minus 1. And then let us consider the term where n is equal to -2. So we'll have plus f of -2. And here k0, 2, n minus 2, z0, so it's 1. Okay, so these here are the two formulas that we will use in our exercises with difference equations, and when the difference equations involve a shifting to the right. We will see later in the course in a few slides that you can obtain these formulas in a very intuitive way. We can do something very similar for shifting to the left. Again, we assume that we have the z transform of the original signal. Remember that f of z is the sum going from k0 to infinity of f of k z minus k. So now we're computing the z transform of the shifted signal to the left, because we assume here that k0 is positive, right? So by definition of the z transform, this is what we obtain, and this is similar to what you have done over here. And we will do a substitution. N is equal to k plus k0, so this is n over here. And obviously k is going to be n minus k0, so you can plug this in, and this is why you have here a z minus n and a z minus minus, so plus k0, right? In here k ranges from 0 to infinity, so n will range from k0 to infinity. So our z transform is equal to this sum over here. And what we would like is construct a z transform, and what is annoying is this index k0 here that is positive. So what we'll do is, well, write a sum from 0 to infinity, and obviously we'll have too many terms, so we'll have to subtract them. So this is this sum from 0 to infinity. We have taken out the z to the power k0. It does not depend on n, and this is what you obtain. And you see, of course, here that this is the original z transform of the original signal. And here we have made or taken too many terms, so we need to subtract all the terms that are in here, going from 0 to k0 minus 1, right? So we have now the z transform of the signal shifted to the left by k0 positive, and the Z transform has exactly the same region of convergence as the original signal with additional restrictions at infinity, and this is coming from this Z to the power k0 over here. If the initial conditions are 0, this term will disappear and you'll end up with this relation over here. In the exercises, we'll have to use this time shifting property with k0 is equal to 1 and k0 is equal to 2. So let's apply the formula to this case. So the Z transform of the signal shifted by a 1 to the left will be, this is f of z, remember? It will be z f z, and in this sum, since k0 is 1, there will only be one term corresponding to n is equal to 0. So minus f0 z0, and here k0 is 1, so f0 z, right? So let's apply this when you consider a sequence that has been shifted to the left by 2. So this is again fz, k0 is 2, so it's z square f of z. Now there will be two terms in this one, the one that is equal n equal to 0 and n is equal to 1. So let us first take the one that corresponds to n is equal to 0. It will be f0 z0, right, z square. So we have z square, and now let us consider the term that is coming from n is equal to 1. So we'll have f of 1. We'll have z minus 1 z squared, so this is z over here. These are the two formulas that you'll have to use in exercises where you have to solve difference equations and there is time shifting to the left. So we have computed the Z transform of time shifted signals, and we have done this in a rather mathematical way. Well, there is also a more intuitive way that we'll present now, and this is maybe the way to go at the time of the exam when you look for the Z transform of time shifted signals. So the original signal will always be here at the top, and it's this signal f of k, and of course we are interested in its one-sided Z transform, so we have to multiply this signal by u of k. And of course what you should know is, and this I expect you to know at the time of the exam, is the definition of the Z transform. It's this sum that ranges from 0 to infinity of fk z minus k. If you write it down, the term corresponding to k is equal to 0 is f0. The one that corresponds to 1 is f1 z minus 1. The next one is f2 z minus 2, and so on. So if we shift this signal by 1 to the right, this is what you obtain, and you can see things visually, right? What you have now here at the index that is correspond to k is equal to 0 is what you had here at the index k minus 1. So if we take the Z transform, and again it's the one-sided Z transform of this shifted signal, this is what you obtain. And again you can have a look at the different terms. K equals 0, this one, f of minus 1 z0, k equals 1, this one, f of 0 z minus 1, k equals 2, f of 1 z minus 2, and so on. What you can now do is compare what you see over here and what you see over here. And you can observe that if you multiply, remember that this is f of z, right? If you multiply f of z by z minus 1, you will have all the terms that you have to the right of this one. Okay, you have what you have to the right of this one. So this is z minus 1 f of z, and what you have to add is f of minus 1. So you can use this same trick if you shift the sequence by 2 to the right. So observe what is happening, and what you can do is now again compute this one-sided z transform of this shifted signal. This is what you obtain over here. Again, you'll have terms corresponding to k is equal to 0, f of minus 2 z0, this one, k is equal to 1, k is equal to 2, k is equal to 3, and so on. Again, observe that this is here f of z, and observe that what you have to in this direction here is z minus 2 f of z, right? This is this sequence here multiplied by z minus 2. So this is what you've got over here, and what you have to add is these two terms over here. Well, this also works for time shifting, but to the left. Observe here that we have our original sequence with the z transform that has been defined previously, and what we see over here, and this can be seen visually, is the same sequence but shifted to the left by 1. Again, what we can do is compute the one-sided z transform, and by a simple use of the definition of this one-sided z transform, we obtain this relation over here. So again, we consider all the terms. The term that corresponds to k is equal to 0, k is equal to 1, k is equal to 2, and k is equal to 3, and of course you can continue, right? So you can kind of see that you can obtain this thing here from what is over here by simply multiplying by z. Okay, so if you take this one, you multiply by z, you have this, but there is one term that is too many and that you have to subtract. So the z transform here is z times the original z transform minus the term that is added. If you multiply this one by z, you have here a term z f0 that is not in here, so you should subtract it. So if we now shift by 2 to the left, this is what you see, and you will see it visually. So indeed, this sequence over here is, well, this original time sequence is shifted by 2 to the left. So this is the z transform of our original sequence, and now we are looking for the z transform of this sequence that has been shifted by 2 to the left. As usual, we are using this one-sided transform, so we are multiplying by the unit step to make everything, well, causal, and by definition of the z transform, this is what we obtain. Again, we consider the terms k is equal to 0, k is equal to 1, k is equal to 2, and k is equal to 3, and of course you can go on. Observe that you can obtain what is over here by taking what is over here and multiply by z square, except that you'll have two additional terms that are not in here. It's f0 z square and f1 z, so of course you have to subtract them, and this is how you obtain the z transform of a signal that has been shifted by 2 to the left. In summary, these are the time shifting properties of the z transform that you will use. You have two properties for shifting to the right by 1 and by 2, and two properties for shifting to the left by 1 and by 2. We've kind of seen that you can obtain these formula using more mathematical arguments, and you can also obtain this formula in a more intuitive way. Anyway, please do not learn these formulas by heart. Be able to find these formula using the arguments that have been given here in the course. At least you will not make mistakes at the beginning of an exercise at the time of the exam. Observe that if you shift a signal to the right, to compute the z transform, you need initial conditions that are to the left of 0. So for instance, if you shift by 1 to the right, you need the initial condition in f of -1, you need 1 initial condition, and if you shift to the right by 2, you need the initial conditions in -1 and -2, and you therefore need 2 initial conditions. And if you shift a signal to the left, you will need to compute the z transform, the initial conditions in 0 and to the right of 0. For instance, if you shift the signal to the left by 1, you need the initial condition in 0, so you need 1 initial condition. And if you shift the signal to the left by 2, you need the initial conditions in 0 and 1. Okay, so you need 2 initial conditions. We know from the time shifting property that with 0 initial conditions, the z transform of a signal f of k that has been shifted to the right by k0 can be obtained from the original z transform of the unshifted signal multiplied by z minus k0. So assume now that we have a system that has transfer function z minus 1. We have not yet introduced the transfer function in the context of discrete time systems, but you can imagine from what you have seen in the Laplace domain that the transfer function will link the input x of z to the output as follows. We'll come back to that later. So if a system is described by a transfer function z minus 1, then you have this relation over here. And from what you see over here, if you do the inverse z transform, you see that, well, the output and the input are linked as described over here. So you can see here that the output is simply the input shifted by 1. This is why the operator z minus 1 is called the unit delay operator. This should not come as a surprise. So if we go back to the Laplace domain and that we have that the Laplace transform of f of t is f of s, then we know that the Laplace transform of a time shifted signal is, well, it's f of s times exponential of minus theta s f of s. Let us now assume that we sample the signal with a period ts and that theta is k0 times ts. right? Well, then we can have a look at this quantity over here. It's e to the minus k0 ts s, right? Remember also that z is defined as an exponential of tss, okay? This is the link between the s-plane and the z-domain. So you can see that this quantity over here is simply z minus k0. And this again shows that z minus 1 is the unit delay operator. The next property of the z transform involves the derivative of f of z. Remember that f of z is the z transform of the sequence f of k. We assume again a one-sided z transform, so we have f of k z minus k, right? So if we take the derivative of this quantity with respect to z, this is what you obtain, and this here, if you compute it, it's minus k z to the minus k minus 1. Okay, so you can rewrite this, and this is what we obtain. And why do we rewrite this? Well, because you see here that this is a z transform. It's the z transform of k fk u of k, right? So if you want to obtain this z transform, well, you can obtain it from the derivative of f of z, and you have to, well, you have to take this one and take it on the other side. So you have to multiply this derivative of f of z by minus z. So from this property of the derivative of f of z, we can compute the z transform of k f of k uk, knowing the z transform of the sequence fk uk. So what we can do is use this property to obtain this z transform over here. So you can see here that f of k is alpha k, so this means that we need the z transform of f of k uk, so alpha k uk, and we have shown previously that this is 1 over 1 minus alpha z minus 1, or equivalently, if you use the variable z, z over z minus alpha, and the region of convergence was that the modulus of z is larger than alpha, right? So we can use this property over here to obtain this z transform. So it's minus z times the derivative of, and this is f of z over here, it's minus z times the derivative of this one with respect to z. This is the z transform of this one when you use the variable z minus 1, but it's of course easier to work with the variable z. So this is f of z over here, and if we compute the derivative of f of z with respect to z, what we have is z minus alpha squared, at the numerator z minus alpha times the derivative of the numerator, it's 1 minus z times the derivative of the denominator, and it's a 1 also. So the derivative is minus alpha z minus alpha squared, right? So if you multiply this derivative now by minus z, this is what you obtain, and the region of convergence will also be that the modulus of z is larger than alpha. You have to look at the pole, and you construct a circle of radius alpha. We assume here that alpha is real, but it would work also with complex alpha, but then you would have to take the modulus, and you construct a circle on this modulus of alpha, and the region of convergence is of course what is outside of the circle. So what you have right now is all the z transform that you can obtain in an exercise. So the z transform of the unit impulse delta k. So this is 1, and the region of convergence is the z-plane. We have the z transform of the unit step. This is z over z minus 1, and the region of convergence is z in modulus larger than 1. We have the z transform of the exponential signal. This is z over z minus alpha, and the region of convergence is z larger than alpha. We assume here that alpha is real, and the one that we have here below is the z transform of k alpha k uk, and this is alpha z, z minus alpha squared, and the region of convergence is z larger than alpha. Okay, so these are the z transform that you're likely to encounter in the exercises. Do not forget that for a sequence of finite supports, it might be interesting to use simply the definition of the z transform, which is the sum when k ranges from 0 to infinity of fk z minus k. So this you should know in order to, well, not know, it's you should be able to find it back, right? And you should also be able to find back the, well, time shifting properties that will allow you to solve different equations and to make sure that these initial conditions enter into play. So the next property is to take the z transform of a signal that is damped. Okay, so we again assume that we have the one-sided z transform of the signal f of k, and then we look for the z transform of this same signal but that is damped by alpha k. Well, it might be also that if alpha is larger than 1, it's not damping, but that you multiply by something that is diverging. So by definition of the z transform, this is what you obtain, right? And what you can do is either rewrite this as what is here and what is over here. You can see that alpha k z minus k, you can write it as, well, z over alpha to the power minus k, but you can also write it as alpha z minus 1 to the power k. So what you see here is again a z transform. This is a z transform, but you see that here it's the original z transform where z has been replaced by z over alpha, and here it's this original z transform where z minus 1 has been replaced by alpha z minus 1. So here you replace z by z over alpha, and here you replace z minus 1 by alpha z minus 1. Of course, there will be an influence on the region of convergence, and this region of convergence will be multiplied by the modulus of alpha. So let us apply this to an example, and remember that we have seen that the z transform of a unit step is 1 over 1 minus z minus 1, or this is when you work with the variable z minus 1, or it is z over z minus 1. This is simply obtained by the definition of the z transform, and remembering that the geometrical series says that this sum over here is 1 over 1 minus q when the modulus is smaller than 1. So this is why the region of convergence is of course outside the unit circle modulus of z is equal to 1. So the region of convergence is here z larger than 1. So what we can do now, this will play the role of f of k uk. We can multiply now with this exponential signal, and we'll assume here that it's a real exponential signal. And from the previous property we have seen that you have to take the original z transform, and if you're working in z minus 1, you replace z minus 1 by alpha z minus 1, and if you're working in using the z variable, you have to replace z by z divided by alpha. And you see that in both cases you obtain what is expected. Also, the region of convergence has to be multiplied by the modulus of alpha. Here alpha is real, so we have a region of convergence that is z modulus of z larger than alpha. And this is indeed consistent with the previous results.